This prototype demonstrates the robust 6G work package 4 components for AI-driven, multi-layer, zero-touch security. The solution makes uses of semantic reasoning and GenAI for assisted security service composition and incident response playbooks generation. Moreover, monitoring and actuation are multi-layer, working at network, application, and physical layer. The zero-touch component is provided by security automation, security closed loops, embedding cacao playbooks for automated responses. The zero-touch security platform is composed of a zero-touch security orchestrator for security service composition, a GenAI 4-SOR component for playbook generation, a programmable monitoring platform for multi-layer data monitoring, a secure resource orchestrator for security functions lifecycle management, and a security closed-loop manager for the lifecycle management of security automation. The platform is able, once a security service level agreement is received, to deploy and configure a security service composed of several security functions and security closed loops. Once the service is active, the programmable monitoring platform collects the data and provides that to the security service, who is able to actuate on the target, providing zero-touch remediation to the identified attack. In this example, the deployed security service is able to detect and remediate to threats on a smart office. In this, ThingsBoard is used as IoT platform, where HVAC devices are hosted. An attacker is able to brute force the platform credentials and compromise the HVAC logic, causing discomfort of the inhabitants. Once the security service is deployed, the programmable monitoring platform starts collecting both network traces and IoT alerts and provides them to the security service. In this case, the security service is composed of a single security closed loop and an OpenC2 ThingsBoard actuator as security function. Once the attack is spotted, the security service is capable of remediate to it and harden the environment to avoid future attacks. As first step, the zero-touch security platform is set up by an administrator, who loads the ontology manager, catalog manager, secure resource orchestrator, and security closed-loop manager. The security orchestrator ontology is loaded with the zero-touch security orchestrator T-box, while the knowledge graph is loaded with the EuBox. The EuBox represents the semantic model that is used by all the other components of the zero-touch security orchestrator. It described the supported class of attacks along with the information models of the supported security functions and target environments. In the example, the password brute force class of attacks is expanded, showing the related alerts and activities. Moreover, the security functions that are suited to spot or remediate this kind of attack are linked through semantic reasoning based on the needed capabilities. Respecting the EuBox, all the available security functions and target environment are loaded in the security catalog. In this case, the Smart Office infrastructure hosts 3 different environments: Docker, Kubernetes, and ThingsBoard, and an already deployed security function, the programmable monitoring platform. The catalog provides the list of all the available and ready-to-be deployed security functions and is consulted by the Security Context Manager to provide the right functions and actuators for security service composition. For all the security functions, the complete manual for usage is stored in the catalog. The available target environments that can be used for security service orchestration are registered in the Secure Resource Orchestrator. In this case, the Smart Office Kubernetes cluster is registered. Moreover, all the templates of security functions and security closed-loop functions are registered in the Secure Resource Orchestrator. These components represents the dynamically orchestrable components of the zero-touch security platform that can be used to compose security services and automations. In the Security Closed-Loop Manager, the descriptors of security closed-loop functions are onboarded and used to compose security closed loops. Each loop is composed of 1 to 5 functions: monitoring, analysis, decision, execution, knowledge. In robust 6G, 2 different types of security closed loop can be associated with a security service. A rule-based security closed loop where alerts are provided directly by the programmable monitoring platform, and an AI-based security closed loop, where the programmable monitoring platform gathers data that are then provided to AI algorithms for analysis. For this scenario, the smart office is set up with 3 sensors. A presence sensor following office opening days/hours. A temperature sensor providing both external and internal readings. And an HVAC actuator, having a fixed schedule to keep a comfortable temperature. These devices are assigned to a customer. HVAC is equipped with static rules to spot HVAC system misbehavior using the Things Board rule chains management. A dashboard is provided to the user to monitor the sensors and override the default configuration of the HVAC. The security service request starts from a security service level agreement specifying the requested activities of network and IoT monitoring and the metrics related to automated responses. In this case, the zero-touch security platform is asked to provide a security automation capable of enforcing a password policy providing a password entropy of at least 100 bits. Once the security service level agreement is submitted, the security context manager validates it using the ontology and provides to the policy manager the list of all the available, deployable, and configurable security services, used as scoped infrastructure context for playbook generation. The GenAI gateway forward this context to the GenAI Forcor crew. The crew of agents starts to analyze the context using expert agents. As first step, the Cyber Threat Intelligent Analyst agent analyzes all the possible attack vectors given the provided infrastructure context. This agent is capable of identifying all the possible attack vectors that can be used to compromise the target infrastructure. Given the identified attack vectors, an agent specialized in OASIS Cacao and OpenC2 standards starts generating mitigation plans for each of the provided attack vectors. In this process, among all the others, a Cacao playbook to remediate brute force attacks on Things Board is generated. This playbook is composed of 4 consecutive steps. First, unassign devices from the user. Second, suspend the user account. Third, enforce a new password policy with entropy GT100B. Fourth, send an email to the user to reactivate their account. Finally, the security service composed of the programmable monitoring platform already deployed and properly reconfigured, an OpenC2 actuator for the Things Board environment, and a rule-based security closed loop embedding the generated playbook is deployed in less than 30 seconds by the zero-touch security platform. As first step, the analysis function of the security closed loop configures the programmable monitoring platform to monitor Things Board alerts and network traffic. Network monitoring is provided via T-Shark and Snort3 equipped with community rules. Once the PMP is properly configured, the analysis stage starts listening on the PMP Kafka topics for alerts. Now the security service is active and ready to remediate to threats. In this scenario, user password can be easily found using a credential stuffing attack via the open source Zatonet file. With this setting, after less than 6 minutes the password is found. Once the credentials are retrieved, the attacker logs with the password on the user dashboard, and is capable of improperly starting the HVAC, causing economic harm and user discomfort. The analysis stage of the security closed loop receives the alerts from the programmable monitoring platform and starts the remediation process. The decision function validates the playbook and the execution function executes it using the ThingsBoard OpenC2 actuator. The 4 different steps of the playbook are correctly executed: unassigning the device, disabling the user account, setting a more robust password policy, and sending an email to the user to reactivate the account. The HVAC device is correctly unassigned from the customer. The new password policy is correctly set up to guarantee the right amount of entropy. And finally, the account activation link is sent to the user, who is now forced to respect the new password policy.